Right now, somewhere in this galaxy, an intelligent civilization may be staring at the sky, wondering if anyone else exists. They may have cities, technology, perhaps even starships. But here is what nobody wants to hear. It does not matter. Even if 1,000,000 civilizations are scattered across the Milky Way right now, the laws of physics have built a prison around every single one of them. Not a prison of ignorance or primitive technology, a prison of distance, energy, and time so absolute that no amount of advancement can break through it. This is not about whether aliens exist. This is about why the universe itself makes it effectively impossible for any of them to ever reach Earth. The barrier is not intelligence. The barrier is reality. If you want to understand the one argument about alien life that almost nobody talks about, the one built not on belief but on raw physics, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. Look up at the night sky on a clear evening. Find two stars that appear close together, nearly touching, like twin jewels pressed into dark velvet. Your eyes tell you they are neighbours. Your brain processes them as nearby objects separated by a small gap. This is the most dangerous lie the universe tells. Those two stars might be separated by 50 light years. They might not even exist in the same spiral arm of the galaxy. One might be a red dwarf burning dimly 6 light years away, the other a blue supergiant blazing from 800 light years out. The night sky flattens the universe into a dome, collapsing trillions upon trillions of miles into a flat canvas that your retina processes as a field of twinkling dots. Every civilization that ever looked upward faced this same illusion. The stars appear reachable. They appear close. They are not. This illusion matters because it is the foundation of every casual assumption about alien visitors. When someone imagines an advanced extraterrestrial civilization traveling to Earth, they imagine a journey. A long one, sure. Difficult, absolutely. But fundamentally a journey with a beginning, a middle, and an arrival. The night sky encourages this thinking. It makes the stars look like destinations on a map, like cities connected by highways. In reality, the space between stars is nothing like a highway. It is an ocean so vast that calling it an ocean is itself an understatement. So extreme it borders on meaningless. The Pacific Ocean stretches roughly 11,000 miles at its widest point. The distance to the nearest star stretches 25 trillion miles. The Pacific Ocean fits inside that interstellar gap more than 2 billion times. Try holding that number in your mind. 2 billion Pacific Oceans laid end to end, and you still have not reached the closest star to our Sun. This illusion persists because human perception evolved for an entirely different purpose. Our ancestors needed to judge the distance to a predator, the reach of a spear throw, the width of a river crossing. The human visual system is calibrated for distances measured in feet, miles, perhaps hundreds of miles, on a clear day from a mountaintop. Nothing in our evolutionary history prepared us to intuitively grasp distances measured in trillions of miles. When we look at the night sky, our brains do what they have always done. They simplify, they flatten, they make the incomprehensible appear manageable, and this cognitive shortcut has quietly distorted every popular conversation about whether aliens could visit Earth. Start with the closest star system to Earth. Alpha Centauri sits 4.24 light-years away. That number sounds modest. 4.24. You could say it in under a second. But a light-year is not a human unit of measurement. It is an astronomical abstraction that compresses incomprehensible distance into a tidy label. 1 light-year equals approximately 5.88 trillion miles. Multiply that by 4.24, and Alpha Centauri sits roughly 25 trillion miles from Earth. 25 trillion. If you started counting to 25 trillion at one number per second, never pausing to sleep or eat or breathe, you would need nearly 800,000 years to finish counting. You would begin before anatomically modern humans had fully spread across Africa, and you would still be counting today. Every pharaoh would rise and fall. Every empire would build its monuments and crumble to dust. Every war would be fought and forgotten, and you would still be counting, still nowhere near finished. 25 trillion miles represents the shortest possible interstellar trip from our solar system. This is not the average distance to a star. This is the closest one, the galactic front door, the nearest neighbour, and it is so far away that no human object has ever crossed more than a trivial fraction of the gap. Consider Voyager 1. Launched in 1977, it is the farthest human-made object from Earth. Voyager travels at approximately 38,000 miles per hour, which is fast by any earthly standard. A bullet from a high-powered rifle moves at about 1,700 miles per hour. Voyager is roughly 22 times faster than a bullet. It has been flying for over 4 decades, without stopping, without slowing, without deviating from its outward trajectory. In all that time, Voyager 1 has covered about 15 billion miles. That sounds impressive until you measure it against the interstellar scale. 15 billion miles is less than one single light day. Not one light year, one light day. Voyager has not yet crossed the distance that light covers in 24 hours, and a light day is 1/365th of a light year, and the nearest star is over 4 light years away. At its current speed, Voyager 1 would require approximately 73,000 years to reach Alpha Centauri. 73,000 years. Human civilization in its entirety, from the first agricultural settlements in Mesopotamia to the smartphone in your pocket, spans roughly 12,000 years. Voyager would need 6 times the entire length of recorded human history to reach the closest star, and when it arrived, it would not stop. It carries no braking mechanism. It would sail past Alpha Centauri and continue into the void, a frozen relic tumbling through darkness with no destination and no purpose. It would join the interstellar medium as a piece of cosmic debris, slowly cooling to the background temperature of space, carrying a golden record that no one would ever play. This is the reality of interstellar distance, not the sanitized version from science fiction where ships jump between stars in minutes, not the Hollywood version where a montage bridges the gap between launch and arrival. The real version. The version where our fastest spacecraft needs 73 millennia to reach the house next door. If an alien civilization launched a probe at comparable speeds toward Earth from Alpha Centauri, we would wait longer than human civilization has existed for it to arrive. And Alpha Centauri is the closest possible starting point. Now scale outward. Alpha Centauri is 4.24 light-years away. The star Sirius, the brightest star in the night sky, sits 8.6 light-years out. That is roughly 50 trillion miles. Vega is 25 light-years away, or about 147 trillion miles. Betelgeuse, the red giant marking Orion's shoulder, lies approximately 700 light-years from Earth. Converting that number into miles produces a figure so long that writing it out would fill a line of text across your entire screen. These are all stars within our own galaxy, not exotic, far-flung objects at the edge of the observable universe, just ordinary stars in our local galactic neighborhood, and the distances between them are already measured in ranges that make Voyager's 4-decade journey look like a footstep on a continental hike. The Milky Way galaxy itself spans approximately 100,000 light-years from edge to edge. That is roughly 588 quadrillion miles. Our solar system sits approximately 26,000 light-years from the galactic center, embedded in a minor spur of the Orion Arm, about 2/3 of the way out from the core. Light, leaving from one side of the galaxy, would need 100,000 years to reach the other side. Not a spacecraft. Light, the absolute fastest thing in the universe. The cosmic speed limit that nothing with mass can ever reach. Even light, traveling at 670 million miles per hour, needs 100,000 years to cross our single galaxy. A human lifespan is roughly 80 years. Light crosses the galaxy in a time span equivalent to 1,250 consecutive human lifetimes. Each of those lifetimes would begin and end in total darkness between stars, surrounded by void, with the destination no closer to the naked eye than it was at the start. And the Milky Way is just one galaxy. The nearest major galaxy, Andromeda, lies approximately 2.5 million light-years away. The observable universe contains an estimated 2 trillion galaxies, scattered across 93 billion light-years of space. These numbers exist so far beyond human intuition that they function as abstractions rather than descriptions. No human mind can genuinely picture 93 billion light-years. We can write the number. We can calculate with it, but we cannot feel it. The universe is built at a scale that renders human experience irrelevant. Here is where this matters for the question of alien visitation. When people imagine extraterrestrial civilizations visiting Earth, they rarely think about where those civilizations would actually be. The galaxy contains roughly 400 billion stars. Many of those stars host planetary systems. NASA's Kepler mission confirmed that planets are common, with most stars hosting at least one world and many harboring several. Some percentage of those systems may contain worlds in the habitable zone, the orbital distance where liquid water could exist on a planet's surface. The probability of intelligent civilizations existing somewhere in the Milky Way is not zero. It might even be reasonably high. But the distribution of those civilizations across galactic space creates a problem that optimism cannot solve. If intelligent civilizations are rare, emerging around perhaps 1 in every 10 million suitable star systems, then the nearest alien civilization might be thousands of light-years away. Not 4 light-years. Not 40. Thousands. If civilizations are more common, perhaps 1 in every 100,000 suitable systems, the nearest might still be hundreds of light-years distant. The galaxy is so enormous and stars are so widely scattered that even a generous estimate of alien abundance places most civilizations at distances that are functionally unreachable. The math does not care about hope. It cares about geometry. And the geometry of a disk, 100,000 light-years wide with stars separated by an average of 4 to 5 light-years, leaves every potential civilization marooned on its own tiny island in a sea of emptiness. Picture this. Shrink the entire Milky Way galaxy down to the size of the continental United States. At this scale, each star becomes a grain of fine dust, barely visible to the naked eye. Our solar system and Alpha Centauri would be 2 grains sitting about 4 inches apart. That seems manageable. But the next nearest sun-like star with a potentially habitable planet might be several feet away. A civilization 1,000 light-years distant would be located in a different state entirely. 5,000 light-years would place them across the country. And the galaxy's full extent, 100,000 light-years, stretches from coast to coast. The galaxy looks crowded on a poster. In reality, it is defined by the emptiness between those scattered grains. Most of the map is blank. Most of the space contains nothing at all. Even if they exist, the universe itself prevents them from getting here. This is the central truth that every discussion about alien visitation must confront before anything else is considered. Distance is not merely an inconvenience for interstellar travelers. It is a wall. Not a wall that clever engineering can tunnel through or sufficient energy can blast apart, but a wall built into the geometry of space-time itself. The space between stars is real, physical, and enormous. It must be crossed mile by mile, year by year, and there are trillions upon trillions of those miles between any 2 stellar neighbours. The emptiness between stars is also genuinely empty in ways that are difficult to appreciate from the surface of a planet teeming with life. The interstellar medium, the material that fills the gaps between star systems, has a density of roughly 1 atom per cubic centimetre. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimetre. The interstellar medium is roughly 25 quintillion times less dense than the air in your lungs. It is a vacuum more perfect than anything humans can create in a laboratory. It is cold, hovering just a few degrees above absolute zero. It is dark, illuminated only by the faint glow of distant stars. It is featureless, offering no landmarks, no waypoints, no reference frames for navigation. A spacecraft traveling between stars would spend decades or centuries surrounded by absolutely nothing, traversing a void so complete that the nearest significant object in any direction would be trillions of miles away. This void creates practical problems beyond mere isolation. Navigation across interstellar distances requires extraordinary precision. At the scale of light years, even tiny errors in trajectory compound into enormous deviations over time. A navigational error of 1/10,000th of a degree at departure translates into missing the target star system by billions of miles at arrival. That is not a rounding error. That is the difference between reaching a solar system and sailing past it into empty space, with no possibility of return. Correcting course mid-journey requires energy, which requires fuel, which adds mass, which requires more energy to accelerate. Every correction feeds back into the same punishing loop. There is also the matter of detection. Finding Earth from interstellar distances is not like spotting a lighthouse from a ship at sea. Earth is a tiny rock orbiting an unremarkable star in the outer suburbs of an ordinary spiral galaxy. It has a diameter of roughly 8,000 miles, which is effectively invisible from even a few light years away. It reflects a minuscule fraction of the sun's light. Its strongest distinguishing feature, the oxygen-rich atmosphere that hints at biological activity, produces spectral signatures so faint that detecting them across interstellar distances pushes the limits of any conceivable telescope technology. Earth's radio emissions, which have been leaking into space since the early 20th century, form a bubble of detectability roughly 200 light-years in diameter. That bubble encompasses perhaps a few 100,000 stars. It sounds like a large number until you compare it to the 400 billion stars in the Milky Way. Our radio bubble covers less than 1/1,000,000th of the galaxy's volume. Beyond that radius, Earth is electromagnetically silent, invisible. A civilization 1,000 light-years away would have no way to know we exist, because our signals have not reached them yet and will not for another 900 years. And even when those signals do arrive, they will be so faint, so diluted by the inverse square law governing electromagnetic radiation, that they will be virtually indistinguishable from the background noise of the cosmos. This detection problem works in both directions. If alien civilizations are broadcasting signals, those transmissions weaken with distance according to the same inverse square law. A signal that is powerful at its source becomes 4 times weaker at double the distance, 9 times weaker at triple the distance, 16 times weaker at quadruple. By the time a radio transmission crosses hundreds of light years, it has spread across such an enormous volume of space that the energy arriving at any particular point is infinitesimal. Distinguishing an alien signal from the natural radio emissions of stars, pulsars, and cosmic background radiation at such distances requires either impossibly powerful transmitters or receivers of a scale that defies practical construction. The universe does not cooperate with communication any more than it cooperates with travel. Consider the scale from an alien perspective. Imagine a civilization on a planet orbiting a star 1,000 light-years from Earth. They are intelligent, curious, technologically sophisticated. Perhaps they have been exploring their local stellar neighborhood for millennia. They have mapped the nearest dozen star systems. They have sent probes to worlds orbiting their closest neighbors. They know the local geography of their galactic suburb the way we know the layout of our solar system. Now they turn their attention outward. They point their telescopes toward our region of space and see the Sun, an average yellow dwarf star among millions of similar stars in their sky. From 1,000 light-years away, the Sun does not stand out. It does not pulse with unusual signals. It does not exhibit the spectral fingerprints of an advanced civilization. It is one ordinary star lost in a dense field of ordinary stars, no more interesting than any of its neighbors. They cannot detect Earth directly. Resolving a planet the size of Earth at a distance of 1,000 light-years would require a telescope with an aperture stretching hundreds of kilometers across. Even an interferometric array combining the light of thousands of smaller telescopes would struggle to produce anything more than a single pixel of data about a world that small at that distance. They might, with extraordinary effort and extraordinary luck, detect the slight dimming of sunlight as Earth transits the face of the Sun from their vantage point. But this transit method only works if the geometry aligns perfectly, if Earth's orbital plane happens to intersect their line of sight to the Sun. For most observers in the galaxy, this alignment does not exist. Earth is invisible. They cannot detect our radio signals. Those signals departed Earth roughly a century ago, spreading outward at light speed in an expanding shell. That shell has covered approximately 100 light-years, reaching perhaps a few 100,000 nearby stars. Our hypothetical civilization sits 1,000 light-years away. Our signals will not reach them for another 900 years, and when those signals finally arrive, they will have weakened to a whisper. The power of a radio transmission drops with the square of the distance. By the time Earth's strongest broadcasts cross 1,000 light-years, the signal strength at any given point will be billions of times fainter than the cosmic background noise. Detecting it would require a receiver so sensitive and so precisely tuned that building one represents an engineering challenge comparable to the interstellar journey itself. From their vantage point, our entire solar system, everything we have ever known or built or dreamed, is one anonymous dot among 400 billion similar dots. Invisible, unremarkable, lost in the crowd. They have no reason to come here because they have no way to know we are here. And this is not a limitation of their technology. It is a limitation of physics. Light travels at a fixed speed. Information cannot outrun it. Our existence is a secret the universe is keeping from them, and it will continue keeping that secret for another 9 centuries, at which point it will deliver the news as a whisper too faint to hear against the roar of the cosmos. Now suppose they are extraordinary. Suppose they have built telescope arrays spanning thousands of kilometers. Suppose they have mapped every star within 5,000 light-years and catalogued the atmospheric composition of every rocky planet in the habitable zone. Suppose, against staggering odds, they have identified Earth as a world with an oxygen-rich atmosphere, a possible signature of biological activity. They still do not know there is intelligent life here. Oxygen suggests biology. It does not suggest civilization. They would see what Earth looked like 1,000 years ago because the light reaching their telescopes left our planet 10 centuries before. They would see the Earth of roughly 1026, medieval Europe, the Song dynasty in China. No radio signals, no city lights, no spectral evidence of industrial activity. Just a small blue world with an interesting atmosphere, one candidate among potentially thousands of similar worlds scattered across their observable sky. The motivation to cross 1,000 light-years of void to visit one interesting-looking rock among thousands of interesting-looking rocks is not obvious. It is not even rational without evidence that the trip would yield something no closer world could provide. Even if they could somehow identify Earth as a compelling target, even if they detected our oxygen atmosphere or stumbled upon our radio emissions after waiting centuries for them to arrive, they would then face the same crushing distance problem. 1,000 light-years equals approximately 5.88 quadrillion miles. At 10% of the speed of light, a velocity that itself represents an almost unimaginable engineering achievement, the journey would take 10,000 years one way. The civilization that launched the mission would need to sustain interest, funding, political will, and institutional memory for 10 millennia just for the outbound leg. No human institution has lasted more than a few thousand years. Most governments rise and fall within centuries. Most empires are dust within a millennium. The mission would outlive the society that conceived it many times over, and this is the optimistic scenario. This assumes the alien civilization is only 1,000 light-years away, which places them among the closer possible neighbours in a galaxy 100,000 light-years across. If they are 5,000 light-years away, the journey at 10% of light speed takes 50,000 years. If they inhabit a star on the far side of the galactic core, it takes hundreds of thousands of years. If they reside in a different galaxy entirely, the travel time extends into the millions or billions of years. These are not travel durations that any civilization can meaningfully plan for, resource, or survive. Even if they exist, the universe itself prevents them from getting here. There is a common instinct when confronted with these distances to reach for human analogies of exploration. People compare interstellar travel to crossing the Atlantic Ocean in the 15th century, or landing on the moon in the 20th. These comparisons feel natural because they invoke journeys that once seemed impossible, but were eventually achieved through technological ingenuity and human determination. The implication is that interstellar travel will similarly yield to future innovation. Give it enough time, enough effort, enough brilliant minds, and the stars will fall within reach just as new continents and celestial bodies did before. This reasoning contains a fatal flaw. The Atlantic Ocean is roughly 3,000 miles wide. The distance to the Moon is approximately 240,000 miles. The distance to Alpha Centauri is 25 trillion miles. The jump from Atlantic crossing to Moon landing is a factor of roughly 80. Impressive, but within the same broad order of magnitude. The jump from moon landing to nearest star is a factor of over 100 million. These are not steps on the same ladder. They are entirely different categories of challenge, separated by a chasm so wide that the word progress loses its meaning. Crossing the Atlantic required building better ships from existing materials. Reaching the moon required inventing rockets powerful enough to escape one planet's gravity well. Reaching another star requires confronting the fundamental speed limit of the universe, the exponential energy costs of relativistic acceleration, and journey durations measured not in days or weeks but in millennia. The progression from sailing ship to Saturn V rocket is not a precedent for the progression from rocket to starship. It is a comforting analogy that disintegrates the moment you examine the actual numbers. The universe operates on scales that do not care about ambition, intelligence, or technological progress. The speed of light is not a barrier that more advanced physics will eventually overcome. It is a structural property of space-time, woven into every equation that describes how reality functions. Every particle, every wave, every interaction in the cosmos obeys this limit. It is not a wall to be broken through. It is the shape of the room itself. You cannot break through the walls of a room you are made of. The Milky Way might contain thousands of intelligent civilizations right now. Millions of planets might harbor complex life. The galaxy could be teeming with minds that wonder exactly as we do whether anyone else is out there. But every one of those civilizations sits inside its own bubble of isolation, surrounded by trillions of miles of nothing, staring at the same deceptively close stars, facing the same impossible arithmetic. The galaxy is not a neighborhood. It is an archipelago of island worlds separated by oceans that no ship has ever been designed to cross. And those oceans are measured not in miles, but in light years. Not in hours of travel, but in millennia. Every star is a solitary outpost. Every civilization is alone with its own sky. Even if they exist, the universe itself prevents them from getting here. Distance is the first wall. It is the wall you encounter before you even begin to consider the engineering, the energy, or the time. It is the wall that transforms interstellar travel from a question of willpower into a question of physics. And it is a wall that stands equally high for every civilization in the universe, regardless of how intelligent they are, how ancient their culture, or how long they have had to develop technology. The laws of geometry apply to everyone, but distance alone does not make the full case. A sufficiently motivated civilization might look at 25 trillion miles and say, "We accept the scale. We will build faster ships. We will push the boundaries of propulsion. We will aim for the stars and bear whatever cost the universe demands." This is where the problem deepens. Because the cost of crossing interstellar distances is not measured only in miles, it is measured in energy. And the energy required to accelerate any meaningful mass to even a modest fraction of light speed is so staggering, so fundamentally enormous, that it makes the distance problem look like a gentle introduction to the real nightmare. The distances between stars are not large in the way that oceans are large or continents are wide. They are large in a way that breaks every analogy we reach for, a way that turns familiar concepts like travel and journey into abstractions that barely apply. But distance by itself does not make interstellar travel impossible. Distance is a passive obstacle. It simply exists, waiting to be crossed. What makes the crossing functionally impossible is what physics demands in exchange for speed. Because the only way to shrink an interstellar journey from millennia into something even remotely approachable is velocity. And velocity, at the scales required for star travel, costs energy in quantities that would bankrupt entire worlds. This is not a soft barrier. This is not a problem that a bigger engine or a better fuel source gradually solves. The energy requirements for interstellar travel scale in ways that are fundamentally hostile to engineering. They do not grow linearly with speed, they grow exponentially. And that exponential curve is not a feature of our current technology. It is a feature of the universe itself, baked into the equations of special relativity, confirmed by every particle accelerator ever built, and inescapable for any civilization made of matter anywhere in the cosmos. Let us start with the most basic version of the problem. To travel between stars in any time frame shorter than geological ages, a spacecraft must reach a significant fraction of the speed of light. 10% of light speed, often written as 0.1 c, is a common benchmark in serious discussions of interstellar propulsion. At this velocity, a ship would travel at roughly 67 million miles per hour. That is almost 18,000 miles per second. For comparison, the fastest human-made object relative to the Sun, the Parker Solar Probe at its closest approach, reaches approximately 430,000 miles per hour. 10% of light speed is more than 150 times faster than the fastest thing humanity has ever built. It represents a leap in velocity so enormous that no incremental improvement in existing propulsion technology can bridge the gap. This is not a matter of building a slightly better rocket. This is a matter of entering an entirely different regime of physics. Now consider what happens when you try to accelerate an object to this speed. Start with something modest. A robotic probe with no crew, no life support, no artificial gravity. Just instruments, a communication system, a power source, and a frame to hold it all together. Call it 1,000 kilograms, roughly the mass of a small car. To accelerate 1,000 kilograms to 10% of light speed requires approximately 4.5 times 10 to the 17th joules of kinetic energy. Written out, that is 450 quadrillion joules. This number means nothing in isolation, so let us anchor it to something real. A large nuclear power plant produces roughly 1 gigawatt of continuous power. 1 gigawatt equals 1 billion joules per second. Running that plant at full capacity for an entire year produces approximately 31.5 petajoules. So accelerating our tiny probe to just 10% of light speed would consume roughly 14 years of a nuclear power plant's total output. 14 years of a facility that cost billions of dollars to build and powers 1 million homes, funneled entirely into pushing a car-sized object to a velocity that still means a 42-year trip to the nearest star. But let us widen the lens further. The total energy humanity produces in an entire year, from every power plant, every engine, every fire, every solar panel on Earth, amounts to roughly 5.8 times 10 to the 20th joules. The energy needed to accelerate our tiny 1,000 kilogram probe to 10% of light speed is approximately 1/1300th of global annual energy production. For a single probe, with no deceleration capability, no crew, no return trip, just a small machine flung into the void with enough velocity to reach the nearest star in 4 decades. The Hiroshima atomic bomb released approximately 6.3 times 10 to the 13th joules of energy. The kinetic energy of our modest probe at 10% of light speed is equivalent to roughly 7,000 Hiroshima bombs, 7,000 nuclear detonations compressed into the motion of a single small spacecraft. That is the energy price for the cheapest possible interstellar ticket, not for a crewed vessel, not for a round trip, not for a journey to a distant star, just a tiny probe aimed at the nearest star, with no way to stop when it gets there. And we have not yet accounted for the cost of stopping, because a probe that arrives at Alpha Centauri at 10% of light speed will fly past the star system in a matter of hours unless it decelerates. Deceleration requires the same energy as acceleration, applied in reverse. The energy budget just doubled. 14,000 Hiroshima bombs worth of energy for a car-sized robot to visit the nearest star and come to a halt when it arrives. This is the scale of the problem for the simplest conceivable interstellar mission. Everything gets worse from here. The tyranny of the rocket equation governs every spacecraft that carries its own propellant. The equation, first published by Konstantin Tsiolkovsky in 1903, describes a brutal relationship between the velocity a rocket can achieve and the amount of fuel it must carry. The core problem is circular. To go faster, you need more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that additional mass, which adds more mass, which requires more fuel. This exponential feedback loop means that the fuel requirements do not scale proportionally with speed. They scale exponentially. For chemical rockets, which produce exhaust velocities of roughly 4.5 kilometers per second, reaching even 1% of light speed would require a fuel-to-payload ratio so extreme that the spacecraft would need to be almost entirely fuel. Reaching 10% of light speed with chemical propulsion is not impractical. It is mathematically impossible. The amount of fuel required exceeds the mass of the observable universe. This is not an exaggeration. The exponential function grows that aggressively. Nuclear propulsion offers improvements but does not escape the fundamental trap. A nuclear thermal rocket, which heats propellant using a fission reactor, achieves exhaust velocities roughly twice those of chemical rockets. A nuclear pulse propulsion system, like the theoretical Project Orion concept from the 1950s, would detonate nuclear bombs behind the spacecraft to generate thrust. Orion's designers estimated it could reach perhaps 3 to 5% of light speed. Even this extraordinary concept, which required detonating thousands of nuclear warheads in sequence, could not approach the velocities needed for practical interstellar travel. And it carried its own devastating limitations, including the minor issue of requiring a spacecraft the size of a city and a stockpile of nuclear weapons that would make every Cold War arsenal look modest. Fusion propulsion represents what many regard as the most promising theoretical option beyond nuclear pulse concepts. If engineers could build a working fusion reactor that converts hydrogen into helium and channels the resulting energy into directed thrust, it would represent a monumental advance over chemical or fission rockets. Fusion releases roughly 4 times more energy per kilogram of fuel than fission, and hydrogen fuel is abundant throughout the universe. A fusion-powered starship could theoretically achieve exhaust velocities of several percent of light speed, making interstellar missions conceivable on timescales of centuries rather than millennia. But sustained, controlled fusion remains beyond human capability despite more than 70 years of dedicated research and hundreds of billions of dollars in global investment. The fundamental challenge is containment. Fusion requires heating hydrogen isotopes to temperatures exceeding 100 million degrees Celsius, roughly 6 times hotter than the core of the Sun. At these temperatures, matter exists as plasma, a state so energetic that it destroys any physical container it touches. Current approaches use powerful magnetic fields to suspend the plasma in a vacuum, preventing it from contacting the reactor walls. This magnetic confinement must be sustained continuously, with extraordinary precision, while the plasma writhes and twists in chaotic turbulence that has defied reliable control for decades. The history of fusion research is a history of promises deferred. In the 1950s, physicists predicted commercial fusion power within 20 years. In the 1970s, they predicted it within 30 years. In the 2000s, they predicted it within 30 years again. The joke among plasma physicists is that fusion is always 30 years away. This is not because the scientists are incompetent. It is because the physics is genuinely, stubbornly, almost maliciously difficult. Every time engineers solve one instability in the plasma, another appears. Every time they increase confinement time, new energy loss mechanisms emerge. The plasma does not want to be contained. It finds every weakness in the magnetic bottle and exploits it, cooling itself, destabilizing itself, and extinguishing the fusion reaction in microseconds. As of today, no fusion reactor on Earth has produced more energy than it consumed in a sustained, repeatable manner. The International ITER project, the most ambitious fusion experiment ever attempted, aims to demonstrate net energy gain for the first time. Its construction has taken decades, and its budget has ballooned to roughly $25 billion. If successful, ITER will produce approximately 500 megawatts of fusion power for periods of minutes. 500 megawatts sustained for minutes. The energy needed to accelerate even a small interstellar probe requires sustained power outputs millions of times greater, maintained not for minutes, but for months or years of continuous acceleration. The gap between current fusion research and interstellar fusion propulsion is not a gap that the next generation of engineers will close. It is a chasm spanning multiple fundamental breakthroughs, each one of which may or may not prove achievable. Proposing fusion-powered starships today is like proposing skyscrapers during the Stone Age. Not merely ambitious, disconnected from the current state of the prerequisite technologies by an unknowable number of intermediate steps. The most energy-dense fuel theoretically possible is antimatter. When matter and antimatter meet, they annihilate each other completely, converting 100% of their combined mass into energy. According to Einstein's famous equation, energy equals mass times the speed of light squared. No other reaction in physics achieves this efficiency. Chemical combustion converts less than 1/10⁻⁰% of fuel mass into energy. Nuclear fission converts roughly 0.1%. Nuclear fusion converts roughly 0.7%. Antimatter annihilation converts 100%. It is the ultimate fuel, the theoretical ceiling, the maximum energy that physics permits per kilogram of material, and it is still not enough to make interstellar travel easy. To accelerate a 1,000 kilogram probe to 10% of light speed using antimatter propulsion, you would need approximately 500 kilograms of antimatter combined with 500 kilograms of normal matter. That sounds surprisingly reasonable until you learn how much antimatter humanity has ever produced. The total amount of antimatter created by every particle accelerator on Earth across the entire history of physics amounts to roughly 20 nanograms. A nanogram is 1/1000th of a gram. 20 nanograms would not be visible to the naked eye. It would not register on a kitchen scale. It would not register on most laboratory scales. If you gathered together every atom of antimatter that every accelerator has ever produced across every country over every decade of particle physics research, the resulting speck would sit on the tip of a needle and vanish from sight. Producing a single gram of antimatter using current technology would require approximately $25 trillion and roughly 25 million billion watt-hours of energy. To put that in perspective, $25 trillion exceeds the gross domestic product of the United States. The energy required exceeds the annual output of thousands of power plants for 1 gram, a mass you could hold on your fingertip. Producing 500 kilograms of antimatter is not a challenge for the next century or the century after that. It is a challenge that sits so far beyond current capability that placing a timeline on it is meaningless. The entire global economy, redirected entirely toward antimatter production, using every watt of power generated on Earth, would need to operate for millions of years to produce the antimatter required for a single small interstellar probe. You might as well ask when we plan to bottle a star. And 500 kilograms of antimatter is the fuel requirement for a probe the mass of a small car. Not a crewed vessel, not an arc ship, a tiny robotic probe with no passengers, no return trip, and no deceleration capability. Scale to a spacecraft large enough to carry even a small crew of 10 people, along with life support systems, radiation shielding, food, water, waste, recycling, navigation equipment, communication systems, and structural materials. Such a vessel would mass at absolute minimum hundreds of thousands of kilograms. Realistic estimates for a crewed interstellar craft range from 1 million to 100 million kilograms. The antimatter fuel requirements scale proportionally. A 100 million kilogram spacecraft would need roughly 50 million kilograms of antimatter. Producing this quantity would require energy inputs so vast that they exceed the total energy output of current human civilization by many orders of magnitude. The numbers do not merely stretch credibility, they exit the realm of meaningful discussion and enter the territory of pure mathematical abstraction. This is the energy wall. It does not bend. It does not soften with technological progress. It is a direct consequence of physics. The kinetic energy of any object increases with the square of its velocity. As velocity approaches a significant fraction of light speed, relativistic effects compound the problem further. According to special relativity, as an object accelerates toward light speed, its effective mass increases. This is not a metaphor. The object literally requires more energy to accelerate each additional unit of speed. At 90% of light speed, a spacecraft's relativistic mass is approximately 2.3 times its rest mass. At 99% of light speed, it is roughly 7 times its rest mass. At 99.9%, it exceeds 22 times its rest mass. The closer you get to light speed, the more the universe resists your acceleration, demanding exponentially more energy for each incremental gain in velocity. Reaching light speed itself would require literally infinite energy. It cannot be done, not by us, not by any alien civilization, not by any being made of matter anywhere in the cosmos. Even if they exist, the universe itself prevents them from getting here. Let us put aside antimatter for a moment and consider alternative propulsion concepts that do not require carrying on board fuel. The most promising candidate is laser propulsion, sometimes called a light sail or beam-powered propulsion. The concept is straightforward. A spacecraft carries an enormous but extremely lightweight reflective sail. A ground-based or space-based laser array fires a concentrated beam at the sail. Photons from the laser bounce off the sail, transferring momentum and gradually accelerating the craft. No onboard fuel required. The energy source stays at home, which eliminates the tyranny of the rocket equation entirely. This sounds like a solution. It is not. It simply trades one set of impossible engineering constraints for another. The Breakthrough Starshot initiative, announced in 2016, proposed exactly this approach. The plan envisioned a fleet of gram-scale probes, each weighing roughly 1 gram, propelled by a ground-based laser array with a total power output of approximately 100 gigawatts. 100 gigawatts is roughly the total electrical generating capacity of a medium-sized country like the United Kingdom. This entire national energy output, focused into a coherent laser beam and aimed at a sail smaller than a bedsheet, would accelerate a 1-gram probe to 20% of light speed, reaching Alpha Centauri in roughly 20 years. 1 gram. Not a crewed vessel, not even a useful robotic probe by most standards. A chip-sized sensor package weighing less than a paperclip, and it requires the focused energy output of an entire industrialized nation to reach its target star in 2 decades. Scaling this concept to anything resembling a meaningful spacecraft, even a modest 10-kilogram probe carrying a camera and a communication antenna, would require laser arrays producing tens of thousands of gigawatts. More energy than human civilization currently produces, and this approach carries a fundamental flaw that no amount of power can fix. The laser can only push, it cannot pull. A light sail accelerated to 20% of light speed has no way to slow down at its destination. It screams past the target star system in a matter of hours, taking a few blurry photographs before vanishing into the interstellar void. To decelerate, you would need a second laser array at the destination, which means someone has already been there to build it, which means you have not solved the problem, you have merely assumed it away. Some proposals suggest using the target star's own light to decelerate a sail, reversing the craft's orientation as it approaches. This works in principle, but only at extremely low velocities. A sail arriving at 20% of light speed would need to bleed off an enormous amount of kinetic energy. Stellar light pressure is far too weak to accomplish this in the brief window before the craft overshoots the system. The sail would need to be impractically gigantic, thousands of kilometers across, and even then the deceleration would take years, during which the craft overshoots its target by trillions of miles. The physics simply does not close. Every propulsion concept ever seriously proposed for interstellar travel runs into the same fundamental constraint. Moving mass across light years requires energy on scales that are staggering by any civilizational standard. This is true for chemical rockets. It is true for nuclear rockets. It is true for antimatter engines. It is true for laser sails. It is true for fusion drives. The specific numbers change. The underlying reality does not. Interstellar travel demands energy expenditures so vast that they represent a significant fraction of a civilization's entire energy budget, sustained over periods of years or decades, directed at a single mission with no guarantee of return. Here is where the argument takes a critical turn. Everything discussed so far applies to human technology and human energy production. The natural response is to imagine an alien civilization far more advanced than ours. A civilization that has harnessed the full power of its star or developed energy sources we cannot yet conceive. Would such a civilization not find interstellar travel affordable? Would not the energy wall crumble before their superior capabilities? No. And this is the point that casual speculation consistently misses. The energy wall is not an artifact of human limitations. It is a consequence of physics. The kinetic energy required to accelerate mass to relativistic speeds is determined by the mass of the spacecraft and the speed of light. These are constants. They do not change based on who is doing the engineering. A civilization 10,000 years more advanced than humanity still must obey the relationship between kinetic energy, mass, and velocity. They can build more efficient engines. They can harness more total energy, but they cannot reduce the energy required for the trip itself, because that energy is dictated by the laws of mechanics and relativity, not by the sophistication of the engine. Consider an analogy from everyday physics. Lifting a 1 kilogram object 1 meter against Earth's gravity requires approximately 10 joules of energy. This is true whether you lift it with your hand, a pulley, or a robotic arm designed by the most advanced engineers in history. The mechanism changes. The energy requirement does not. You can make the lifting process more efficient. You can waste fewer joules on friction and heat, but you cannot reduce the 10 joules required by the gravitational potential itself. The universe sets the minimum cost. Technology determines only how close you can approach that minimum, never how far below it you can go. The same principle applies to interstellar propulsion. The minimum energy to accelerate 1 kilogram to 10% of light speed is approximately 4.5 times 10 to the 14 joules. No technology can reduce this number. It is set by the mass, the velocity, and the constant speed of light. An alien civilization could theoretically approach this minimum with near-perfect efficiency, losing almost no energy to waste heat or exhaust inefficiency. But they cannot go below it. The floor is set by physics, not engineering. This means that even a civilization capable of capturing the entire energy output of its host star, a Dyson sphere civilization producing roughly 4 times 10 to the 26 watts, would still face meaningful constraints when launching interstellar missions. The energy to accelerate a crewed vessel to relativistic speed would consume a measurable fraction of even this godlike energy budget. not a trivial fraction either. A large interstellar arc, massing millions of kilograms and accelerating to a significant percentage of light speed, would require energy inputs comparable to the total output of a star sustained over a period of days or weeks. A single mission would be an enormous undertaking even for a civilization that has mastered stellar-scale engineering. Launching thousands of such missions, the kind of exploration program needed to systematically visit star systems across the galaxy, would strain resources at a level that makes such programs effectively impractical, even for the most advanced imaginable civilization bound by known physics. Even if they exist, the universe itself prevents them from getting here. The energy barrier does not soften with better technology. Thermodynamics applies everywhere in this universe. It applies to us. It applies to them. It applies to every civilization that has ever existed or ever will exist in this cosmos. There is another dimension to the energy problem that is often overlooked. So far, we have discussed only the energy required for propulsion. But sustaining a spacecraft over interstellar distances demands continuous energy expenditure beyond thrust alone. Life support systems must operate without interruption for years, decades, or centuries. Temperature regulation must maintain livable conditions against the near absolute zero cold of interstellar space. Communication systems must generate signals powerful enough to reach home across light years of distance. Navigation instruments must remain operational throughout a journey, lasting longer than most civilizations endure. Shielding systems must protect crew and equipment from cosmic radiation, high-energy particles, and the micrometeorite impacts that become catastrophic at relativistic speeds. Each of these systems draws power. Each imposes mass. Each feeds back into the propulsion equation, demanding more fuel, which adds more mass, which demands still more energy. The total energy budget for a crewed interstellar mission is not simply the kinetic energy of acceleration and deceleration. It is the sum of propulsion energy, life support energy, shielding energy, communication energy, and every other system that must function continuously for the duration of the voyage. When all these factors are included, the energy requirements climb even further beyond the already staggering propulsion costs. A crewed interstellar mission is not merely an engineering project. It is a sustained industrial operation that must function autonomously, without resupply, without maintenance from external sources, without error, for periods of time that exceed the lifespan of every human institution ever created. And so we arrive at the full scope of what physics demands from any civilization contemplating a journey to another star. They do not face a single challenge. They face a cascade of interlocking challenges, each one individually formidable, each one amplifying the others. More speed requires more energy requires more fuel requires more mass requires more energy, more distance requires more time requires more life support requires more mass. The loop has no exit. It is not a circle that better technology makes smaller. It is a circle whose diameter is set by the physical constants of the universe. You can run around it more efficiently, but you cannot shrink it. This is what separates the energy barrier from ordinary engineering challenges. When humans wanted to fly, they needed to generate enough lift to overcome gravity. That was an engineering problem with engineering solutions. When humans wanted to reach orbit, they needed to achieve a specific velocity against a specific gravitational field. That was a harder engineering problem with harder engineering solutions. When any civilization wants to reach another star, they need to generate energy on a scale that is fixed by the mass of their ship and the immutable speed of light. This is not an engineering problem waiting for a better engineer. This is the universe stating its price, and the price is non-negotiable. Even if they exist, the universe itself prevents them from getting here. Distance sets the stage, energy sets the price. Every civilization that looks at the stars and dreams of crossing the void must eventually do the math. And the math is unforgiving. It does not offer discounts for ingenuity or exemptions for ambition. The energy required to send mass between stars is enormous. non-negotiable, and universal. It applies to silicon-based life and carbon-based life, and any form of life that occupies physical space and obeys the laws of thermodynamics. Every alien civilization in the Milky Way, no matter how ancient or advanced, faces the same equation when they look toward our sun and wonder whether the trip is worth the cost. Most of them, if they exist, have probably done the math, and most of them have probably reached the same conclusion. The cost is real, the distance is vast, the energy is staggering. But suppose a civilization accepts the cost. Suppose they commit the resources of an entire world or an entire star to the construction and launch of an interstellar vessel. Suppose the ship is built, the fuel is loaded, the crew is aboard, and the engines ignite with the fury of a small sun. The ship accelerates. It reaches 10% of light speed. The star behind it shrinks to a point. The star ahead remains a point. The journey has begun, and this is where the problem deepens beyond what distance or energy alone could impose. Because even after paying the impossible energy price, the journey itself introduces a category of obstacles that no engine can overcome and no shield can fully deflect. The obstacle is time. The unrelenting, irreversible, civilization-eroding passage of time. And time, unlike distance and energy, cannot be compressed, stored or traded. It simply passes, and it passes for everyone. The void between stars is incomprehensibly vast. The energy required to cross that void is staggering beyond any civilizational budget. But both of those barriers, distance and energy, are in some sense static. They can be measured, quantified, and placed on a ledger. A civilization could theoretically look at the numbers, accept the cost, and commit. The third barrier is different. It does not sit still. It does not wait on a balance sheet to be evaluated. It moves. It erodes. It degrades everything it touches. The third barrier is time. And time is the cruelest constraint of all, because it attacks not just the mission, but the civilization that launched it, the crew that flies it, the ship that carries them, and the very purpose that justified the voyage in the first place. Begin with a concrete example. 10% of light speed represents an ambitious but theoretically conceivable velocity for interstellar travel. At this speed, a spacecraft covers roughly 67 million miles per hour, fast enough to cross the diameter of Earth's orbit around the Sun in under 3 hours. Fast enough to traverse the entire solar system from the Sun to Neptune in roughly 2.5 days. By any human standard, 10% of light speed is blindingly fast. It is a velocity at which the very concept of distance seems to compress. And yet, at 10% of light speed, a journey to Alpha Centauri, the nearest star system at 4.24 light-years, takes 42 years. One way. Not round trip. Just getting there. A crew that departs Earth at age 30 arrives at age 72, assuming nothing goes wrong, assuming the ship functions flawlessly for over 4 decades, assuming the human body endures the conditions of deep space travel without catastrophic degradation. The return trip doubles the timeline to 84 years. A mission to the nearest star and back would consume an entire human lifetime. The person who steps onto the ship is not the person who steps off. They have aged beyond recognition. Everyone they knew on Earth has aged with them or died. Their children have grown old. Their grandchildren have grown old. The world they left behind has changed in ways they cannot predict or prepare for. They return as strangers to a civilization that may have moved on without them. And this is the best case. Alpha Centauri is the closest star. Most stars in the Milky Way are not 4 light-years away. They are hundreds or thousands of light-years distant. Scale the math accordingly. At 10% of light speed, a journey to a star 100 light-years away takes 1,000 years. A star 500 light-years away takes 5,000 years. A star 1,000 light-years away takes 10,000 years. These are not travel times that any individual can survive. They are not travel times that any crew can endure. They are durations that exceed the lifespan of every empire, every religion, every language, and every cultural tradition that humanity has ever produced. 10,000 years ago, human beings had not yet invented writing. They had not built cities. They had not domesticated horses. The entire arc of recorded human civilization, every book ever written, every war ever fought, every scientific discovery ever made, fits within the travel time for a single interstellar journey at 10% of light speed to a moderately distant star. A civilization that launches such a mission must somehow ensure that the mission continues functioning, continues navigating, continues pursuing its objective across a time span during which everything that defines that civilization will transform beyond recognition or cease to exist entirely. Now reduce the speed. 10% of light speed is extraordinarily ambitious. The energy requirements make clear that achieving even this velocity demands resources on a planetary or stellar scale. A more realistic velocity for a large crewed vessel, accounting for fuel mass, structural limitations, and engineering constraints, might be 1% of light speed. At this speed, roughly 6.7 million miles per hour, the nearest star is 424 years away. A star 100 light-years distant requires 10,000 years. A star 1,000 light-years away requires 100,000 years. At 1% of light speed, interstellar travel does not merely challenge human timescales, it obliterates them. The journey durations enter geological territory. 100,000 years ago, Homo sapiens was sharing the planet with Neanderthals. No human structure, institution, or technology has survived 100,000 years. Nothing we have built has lasted even a fraction of that time. The oldest known constructed building on Earth is roughly 12,000 years old. The oldest known continuous institution is perhaps 5,000 years old. 100,000 years is not a human timescale. It is an evolutionary timescale. Species change over such periods, continents shift, ice ages begin and end. The very concept of a mission lasting this long is not engineering. It is a fantasy disconnected from every observable reality about how complex systems behave over time. This is where the concept of generation ships enters the conversation. The idea is straightforward. If no individual can survive the journey, perhaps a population can. Build a vessel large enough to sustain a self-reproducing community across centuries or millennia. The original crew lives, reproduces, and dies aboard the ship. Their descendants continue the journey. Generation after generation is born, lives, and dies in transit, each one carrying the mission forward until the final generation arrives at the destination. It is an elegant concept in the abstract. In practice, it is a catalogue of cascading failure modes. Start with biology. A generation ship must maintain a genetically viable population across hundreds or thousands of generations. Genetic studies suggest that a minimum viable population for long-term survival, avoiding inbreeding depression and maintaining sufficient genetic diversity to adapt to new environments, requires at least 5,000 to 10,000 individuals. Some estimates place the number higher. This is not a skeleton crew of brave volunteers. This is a small city, housing, feeding, and sustaining 10,000 people in a closed environment for millennia requires a ship of enormous size and complexity. The mass of such a vessel pushes the energy requirements for acceleration into territory that makes the already impossible numbers we have discussed look conservative. But population size is only the beginning of the biological challenge. A closed ecosystem must recycle all resources perfectly: water, air, food, waste. Every molecule must be accounted for and reprocessed indefinitely. No closed ecological system has ever been sustained by humans for more than a few years. Biosphere 2, the most ambitious attempt at a sealed ecosystem on Earth, lasted 2 years before oxygen levels dropped to dangerous lows and the system required external intervention. That experiment involved 8 people in a 3-acre enclosure on the surface of Earth, with gravity, sunlight, and a functioning magnetosphere. A generation ship would need to sustain thousands of people in a sealed metal container, hurtling through a vacuum at millions of miles per hour, with no sunlight, no natural gravity, no magnetic shielding, and no possibility of outside help. For thousands of years, without a single critical system failure. The social dimension is equally catastrophic. Human societies are not stable across millennia. They fragment, reorganize, and collapse with a regularity that historians have documented exhaustively. They experience revolutions, civil wars, ideological shifts, and cultural drift that can transform a community beyond recognition within a few generations. Imagine the reality aboard a generation ship 500 years into a 10,000-year voyage. The original crew is 20 generations dead. Their names survive in a database somewhere, perhaps in a memorial hall that fewer and fewer people visit with each passing century. No one aboard has ever seen a sky, felt wind on their face, or stood beside an ocean. The mission was conceived by people so distant in time that they might as well be mythological figures. Their language has drifted. The words they use to describe the mission's purpose have shifted in meaning through centuries of isolation. Their cultural references have mutated beyond recognition. The music they listened to, the stories they told, the values they held, have all been replaced by new traditions born inside the ship, traditions that would be unrecognizable to the founders. The ship's social structure has reorganized multiple times through crises, power struggles, and ideological movements that the original planners never anticipated. Some factions believe the mission is sacred, a divine mandate inherited from ancestors who saw a truth the current generation must honor. Others believe the mission is a prison sentence imposed by long-dead tyrants who had no right to condemn their descendants to life inside a metal tube. A third faction has developed a religious framework that reinterprets the journey entirely, teaching that the ship has always existed, that the idea of an origin world is a comforting myth, and that the concept of a destination is a heretical fantasy designed to distract the faithful from the only reality that matters, the ship itself. These factions compete for control of resources, of the ship's governance systems, of the educational curriculum that shapes the next generation's understanding of why they exist and where they are going. Some of these conflicts will be resolved through debate and compromise. Others will not. Violence is not merely possible aboard a generation ship over millennia. Given the length of time, the pressure of confinement, and the absence of any external moderating influence, it is statistically inevitable. Now, extend the timeline. 1,000 years into the voyage, 2,000, 5,000. At each milestone, the social pressures intensify. Resources that were abundant at departure have been consumed, recycled, consumed again, and gradually degraded through imperfect recycling. The ship's population has fluctuated through epidemics, famines caused by agricultural system failures, and periods of deliberate population reduction when resources ran scarce. The original governance structure has been overthrown and replaced dozens of times. The mission's purpose has been reinterpreted so many times that it bears no resemblance to the original mandate. The destination star, still thousands of years away, is an abstraction that holds no emotional weight for people who have lived their entire lives and whose parents and grandparents and great-grandparents lived their entire lives inside the same corridors and chambers. The journey is no longer a means to an end. It is the only world anyone has ever known. And the suggestion that this world should someday end, that the ship should stop and its population should disembark onto an alien planet with open sky and unknown dangers, might be met not with excitement but with terror, resistance, or outright refusal. A population confined to a finite space with no external contact, no immigration, no new resources, and no horizon beyond the walls of their vessel faces psychological pressures that no human community has ever been tested against. What happens when birth rates fall below replacement levels because the population collectively decides, consciously or unconsciously, that bringing children into a sealed metal world with no future beyond more sealed metal is an act of cruelty rather than hope? What happens when a critical specialist dies without having trained a successor, and the knowledge needed to maintain a vital system is lost forever? What happens when the ship's manufacturing capability degrades to the point where replacement parts can no longer be produced, and each mechanical failure becomes permanent? These are not hypothetical concerns. They are projections based on observed human behavior in far less extreme conditions. Isolated communities on Earth, communities with access to fresh air, sunlight, and the possibility of leaving, still experience social collapse, violence, and ideological fragmentation within a few generations. Mechanical degradation poses yet another existential threat. No machine lasts forever. Every material degrades over time. Metals fatigue, seals erode, electronics fail, lubricants break down. Radiation damages circuitry and structural components alike. A generation ship must maintain every critical system: propulsion, navigation, life support, power generation, radiation shielding, hull integrity, across timescales that exceed the operational lifespan of any machine humans have ever built by orders of magnitude. The longest operating human-made machines have lasted perhaps a few centuries under favorable conditions on Earth's surface. A generation ship must operate in the most hostile environment imaginable: hard vacuum, cosmic radiation, extreme temperature differentials, micrometeorite bombardment, for thousands of years without resupply. Every component must either be replaced using onboard manufacturing capabilities or designed to endure conditions that no known material can withstand indefinitely. Even if they exist, the universe itself prevents them from getting here. Time does not merely create logistical problems for the travelers, it creates a fundamental disconnect between the mission and the civilization that launched it. Consider a civilization that sends a crewed vessel toward Earth from a star 1,000 light-years away, traveling at 10% of light speed. The journey takes 10,000 years. During those 10,000 years, the home civilization continues to exist, evolve, and change. Technologies advance, social structures transform, values shift. The civilization that launched the mission 10,000 years ago may bear no resemblance to the civilization that exists when the ship arrives. It may have collapsed entirely, leaving behind ruins and silence. It may have transcended into forms unrecognizable to the original planners. It may have developed faster propulsion technologies and sent a second mission that arrives before the first one. The ship becomes an artifact, a relic of an obsolete era, still crawling toward its destination while the civilization that built it has moved on or disappeared entirely. This is not speculation, it is extrapolation from observed patterns. Human technological capability has increased exponentially over the past few centuries. If this pattern holds for any civilization, then a mission launched today using the best available technology will be obsolete long before it arrives. A civilization that launches an interstellar mission faces a paradox. If they wait, their technology improves, and a future mission could arrive sooner. But if they always wait, they never launch. And if they launch now, the mission may be overtaken by a faster ship launched centuries later. This is sometimes called the incessant obsolescence postulate, and it creates a rational disincentive for any civilization to commit resources to interstellar travel. The optimal strategy is always to wait for better technology, but waiting indefinitely means never going at all. Communication delay compounds every one of these problems into something approaching total futility. At interstellar distances, the speed of light imposes a hard limit on information transfer that is just as absolute as the speed limit on physical travel. A radio signal or laser communication beam travels at light speed, which means it takes 1 year to cross 1 light year. A message sent from Earth to a star 100 light years away takes 100 years to arrive. A reply takes another 100 years to return. A single exchange of information requires 200 years. Imagine what a 200-year conversation actually looks like in practice. A civilization launches a mission to a star 100 light years away. 10 years after departure, the homeworld discovers a critical design flaw in the ship's radiation shielding. they immediately transmit a warning with detailed repair instructions. That message, traveling at light speed, chases the ship across the void, but the ship is also moving at 10% of light speed in the same direction. The message gains on the ship gradually, closing the gap at 90% of light speed. It takes roughly 11 years to catch up. By the time the crew receives the warning, they have been flying with degraded shielding for 21 years. The cumulative radiation exposure may have already caused irreversible biological damage. The repair instructions reference tools and materials that were available at launch, but have since been consumed or repurposed. The crew sends a reply explaining their situation and requesting alternative solutions. That reply takes over 11 years to reach home. The engineers who discovered the original flaw are now 32 years older. Some have retired, some have died. The institutional knowledge needed to devise an alternative solution may have migrated to a new generation of engineers who are unfamiliar with the ship's specific configuration. They develop a workaround and transmit it. Another 11 plus years pass. By the time the crew receives the revised instructions, more than 50 years have elapsed since the original flaw was discovered. The crew members who first received the warning are elderly or dead. Their replacements must interpret instructions written for a version of the ship that has been modified and repaired many times in the intervening decades. This is what interstellar communication looks like at 100 light-years, not a conversation. A series of messages in bottles, each one arriving too late to matter, each one referencing a reality that no longer exists. At 1,000 light-years, the situation becomes absurd. A signal takes 1,000 years to arrive. A reply takes another 1,000 years to return. A single exchange of information requires 2,000 years. The civilization that sent the original message may not exist when the reply arrives. The language the message was written in may have evolved into something unrecognizable. The communication channel itself, the frequency, the encoding, the protocol, may have been abandoned centuries ago, replaced by technologies the original senders never imagined. The reply arrives to an audience that cannot read it, transmitted by a sender that no longer exists, about a problem that was either solved or became irrelevant millennia before the response was composed. For a mission in transit, communication delay means total autonomy from the moment of departure for all practical purposes. A ship traveling to a star 1,000 light-years away cannot receive updated instructions from home in any meaningful time frame. Within a few decades of departure, the communication lag renders real-time coordination impossible. Within a few centuries, even slow-paced exchanges of information become impractical. The mission is on its own. Every decision must be made locally. Every problem must be solved without external help. Every crisis must be managed by the crew or the ship's autonomous systems, with no possibility of consultation, reinforcement, or rescue. The ship becomes an isolated civilization unto itself, disconnected from its origin permanently. If the ship encounters a catastrophic problem, no one is coming to help. If the mission succeeds, no one from the launching civilization may be alive to receive the news. Now layer the interstellar medium itself onto this picture. The space between stars is functionally empty in terms of matter density, but empty does not mean harmless. At relativistic speeds, the sparse material scattered through interstellar space becomes a lethal hazard. A grain of dust weighing 1 milligram, striking a spacecraft at 10% of light speed, delivers kinetic energy equivalent to roughly 100 kilograms of TNT. That is a single dust grain, not a rock, not a pebble, a particle smaller than a grain of table salt hitting with the force of a large conventional bomb. The interstellar medium contains roughly 1 dust grain per 100,000 cubic meters in the denser regions near the galactic plane. Over a journey spanning light years, a spacecraft with a cross-sectional area of just a few hundred square meters would encounter thousands of such particles. Each impact would deliver explosive force to the hull. But it is not just individual impacts that threaten the vessel. It is the cumulative effect of trillions of microscopic collisions over years and decades of flight. At 10% of light speed, individual hydrogen atoms, the most common element in interstellar space, strike the hull with energies in the mega-electron-volt range. Each individual atom deposits a tiny amount of energy, but the flux is relentless. Every second, every minute, every hour, every year, for decades or centuries, the front face of the spacecraft is being sandblasted by a stream of particles moving at relativistic velocities. This transforms the sparse hydrogen gas of the interstellar medium into a steady bombardment, functionally equivalent to standing inside a low-level particle accelerator. Over years and decades of exposure, this radiation erodes surface materials at the molecular level, degrades the crystalline structures of metals, damages electronic components through accumulated displacement of atoms within semiconductors, and poses severe health risks to any biological crew through chronic radiation exposure. Shielding against this bombardment is theoretically possible, but demands material thick enough and dense enough to absorb mega-electron-volt level impacts continuously for decades. The mass penalty is severe, and on a vessel where every kilogram already represents an enormous energy investment, the cost of adequate protection may exceed what any realistic design can bear. Cosmic rays present an additional hazard that no shielding can fully eliminate. High-energy cosmic ray particles, primarily protons accelerated to near light speed by astrophysical processes like supernova remnants and active galactic nuclei, penetrate virtually any material. Some of these particles carry energies equivalent to a fast-pitched baseball concentrated into a single subatomic particle. They pass through spacecraft hulls, through shielding, through human tissue, breaking molecular bonds and damaging DNA as they go. Long-duration spaceflight within our own solar system already poses significant cancer risks from cosmic ray exposure. Interstellar travel, lasting decades or centuries, would subject crews to cumulative radiation doses far exceeding safe limits. No known material provides complete protection. Even meters of solid lead merely reduce the flux without eliminating it. For journeys lasting thousands of years aboard generation ships, cosmic ray damage to both biological organisms and electronic systems represents a slow, relentless degradation that compounds with every passing year, never pausing, never reversing, always accumulating. Even if they exist, the universe itself prevents them from getting here. Time is not a resource that can be manufactured. It passes. Civilizations rise and fall. Stars are born and die. The universe does not pause for travelers. There is one more temporal dimension that must be addressed. Relativistic time dilation, a confirmed consequence of special relativity, alters the flow of time for objects moving at significant fractions of light speed. A crew travelling at 90% of light speed would experience time passing at roughly 44% of the rate experienced by observers who remain stationary. A journey that takes 100 years in the reference frame of the home civilization would feel like approximately 44 years to the crew. At 99% of light speed, the dilation factor increases dramatically. The crew would experience only about 14 years for every 100 years that pass at home. This sounds like a solution. If time passes more slowly for the travellers, they could survive longer journeys. And in a narrow technical sense, this is true. A crew travelling at 99% of light speed to a star 100 light-years away would experience only about 14 years of subjective time. They would arrive biologically intact, still young enough to explore their destination. But time dilation solves the problem for the travellers while catastrophically amplifying it for everyone else. While 14 years pass aboard the ship, 100 years pass on the home world. The crew arrives at their destination to find that everyone they knew is dead. The civilization they left behind has had a full century to change, evolve, collapse, or forget about them. Any mission that relies on time dilation to make interstellar travel survivable for the crew simultaneously guarantees that the mission becomes irrelevant to the civilization that launched it. The crew experiences a manageable journey. The home civilization experiences an absence measured in centuries. Messages sent home arrive decades or centuries after departure. Replies, if they come at all, arrive decades or centuries after that. The crew exists in a temporal bubble, aging slowly while the universe ages normally around them. They are not just travelling through space. They are travelling forward through time, arriving in a future that did not wait for them. And reaching 99% of light speed brings us crashing back into the energy wall, magnified to an almost inconceivable degree. The relativistic mass increase at this velocity means the energy required for acceleration is not merely doubled or tripled. It is multiplied by a factor of roughly 7 compared to the rest mass energy budget. The fuel requirements, the engineering tolerances, the shielding demands, everything escalates by nearly an order of magnitude. Time dilation does not come free. It is purchased at the cost of exponentially greater energy expenditure, which is already beyond the budget of any civilization bound by known thermodynamics. This creates a deeply uncomfortable conclusion. At achievable speeds, journeys take so long that missions outlive civilizations. At extreme speeds, time dilation compresses the journey for the crew, but demands energy that makes the trip effectively impossible to launch. There is no sweet spot. There is no velocity at which interstellar travel becomes simultaneously affordable and timely. The universe has arranged its constants with a precision that blocks every attempted shortcut. Every solution to one constraint tightens the others. Reduce travel time and the energy cost explodes. Add shielding against radiation and the mass grows. Increase the mass and the fuel requirement spirals. Extend the mission duration, and the crew, the ship, and the civilization behind it all begin to crumble. No single breakthrough breaks the pattern, because the pattern is not a chain with a weakest link. It is a web where every strand reinforces every other strand, and the web is woven from the fundamental constants of the universe. Even if they exist, the universe itself prevents them from getting here. A civilization 1,000 light-years from Earth that wants to send a mission here must solve every one of these problems simultaneously. They must generate enough energy to accelerate a vessel to a significant fraction of light speed. They must build a ship that survives millennia of operation in the harshest environment imaginable. They must maintain a crew or a self-sustaining population across timescales that exceed the lifespan of every civilization in their own history. They must navigate with precision across distances so vast that errors of fractions of a degree result in missing the target by billions of miles. They must shield against dust, radiation, and cosmic ray bombardment that intensifies with velocity. They must accept that communication with home becomes impossible within centuries of departure. They must accept that the civilization they represent may not exist when they arrive, and they must do all of this for a destination they cannot confirm is worth visiting. At 1,000 light-years, no telescope can resolve a civilization on a planet's surface, and no electromagnetic evidence of our existence has had time to cross the gap. They would be committing 10,000 years of resources and lives to reach a world that, for all they know, is barren rock. Each of these requirements is individually daunting. Together, they form a barrier that does not weaken with technological advancement because the underlying constraints are set by physics, not engineering. Better engines do not shorten the distance. Faster ships do not eliminate radiation hazards. More advanced life support does not prevent social collapse across millennia. Stronger materials do not stop the universal tendency of all organized systems to decay over time. The obstacles are layered, interlocking, and grounded in the bedrock of physical law. There is one final argument that always surfaces at this point in the conversation. It looks at the distance, the energy, and the time, and it says, "You are thinking too small. You are projecting human limitations onto alien civilizations. A civilization millions of years more advanced than us would have technologies we cannot imagine. They would find ways around these barriers that we are too primitive to conceive. They would simply be more advanced." This argument has an intuitive appeal. It feels humble, it feels open-minded, it feels like it respects the vastness of possibility. It is also wrong, and the reasons why cut to the very heart of what the laws of physics actually are. Every barrier explored in this documentary so far, the distance, the energy, the time, invites the same rebuttal. It arrives in conversations, in comment sections, in late-night debates between friends staring at the stars. The rebuttal sounds reasonable. It sounds humble. It sounds like the kind of open-minded thinking that serious people should embrace. It goes like this: you are thinking like a human. You are projecting our limitations onto beings who may have had millions of years to advance beyond us. A civilization that old, that intelligent, that far beyond our comprehension would have solved problems we cannot even articulate yet. They would find a way. They always find a way. This argument feels powerful because it appeals to imagination. It invokes the unknown and weaponizes it against constraint. It says, in essence, that because we do not know everything, anything is possible. But this reasoning contains a flaw so fundamental that it undermines the entire premise. The constraints described throughout this story are not human limitations. They are not artifacts of our primitive technology or our limited understanding. They are properties of the universe itself. The speed of light is not a human speed limit. It is a cosmic speed limit. The relationship between mass, velocity, and kinetic energy is not a human equation. It is a universal equation. The second law of thermodynamics is not a human observation about entropy. It is a law governing every physical process that has ever occurred or ever will occur anywhere in the cosmos. These constraints do not care who is doing the engineering. They apply to carbon-based life, silicon-based life, energy beings, digital consciousnesses, and every other form of intelligence that occupies physical space and manipulates physical matter. The universe wrote the rules before any civilization existed to read them. Begin with the most structured version of the advanced civilization argument. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations based on their total energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the 16th watts for an Earth-sized world. A Type 2 civilization harnesses the entire energy output of its host star, roughly 4 times 10 to the 26 watts for a Sun-like star. A Type 3 civilization harnesses the energy output of its entire galaxy, roughly 4 times 10 to the 36 watts for a Milky Way-sized galaxy. Humanity currently sits at approximately 0.7 on this scale. We do not yet capture all the energy reaching Earth from the Sun, let alone the Sun's total output. The Kardashev scale is often invoked to suggest that sufficiently advanced civilizations would find interstellar travel trivial. A Type 2 civilization commanding the full power of a star should be able to launch starships the way we launch satellites. A Type 3 civilization harnessing an entire galaxy should be able to scatter probes across the cosmos like seeds on the wind. The energy wall described in Part 2 would crumble before such staggering power, or so the argument goes. But this reasoning confuses the total energy available with the energy required for a specific task. A Type 2 civilization has access to enormous power. That is not in question. What is in question is whether that power changes the physics of the trip itself. And the answer is no. The minimum kinetic energy required to accelerate a given mass to a given velocity is fixed by the relationship between mass, velocity, and the speed of light. No amount of available power reduces this minimum. A Type 2 civilization can generate the energy more easily than we can. They can afford the fuel bill more comfortably, but they cannot pay a smaller bill. The bill is set by physics, not by economics. Harnessing the power of an entire star means you can write a bigger check. It does not mean the check is smaller. Consider what this means in practical terms. A crude interstellar vessel massing 10 million kilograms, modest by the standards of any ship, intended to sustain a population across interstellar distances, requires roughly 4.5 times 10 to the 21 joules to reach 10% of light speed. A Type 2 civilization harnessing the full output of its star could generate this energy in a fraction of a second. But this fact is less reassuring than it appears. because energy was never the deepest constraint. The speed of light is 1% of a star's annual energy for a single ship traveling at a modest fraction of light speed. A Type 2 civilization could afford this. But launching a fleet of such vessels, the kind of systematic exploration program needed to visit even a small fraction of nearby star systems, would consume a significant portion of their stellar budget. And each ship still faces every other constraint described in this story. Each ship still takes centuries or millennia to reach its destination. Each ship still faces interstellar hazards, communication blackouts, mechanical degradation, and the slow erosion of time. More energy does not make the ship go faster than light. More energy does not stop the clock. More energy does not smooth the void between stars or sweep away the dust and radiation that fills it. Even a Type 3 civilization, commanding the energy of 400 billion stars, faces the same structural constraints multiplied across a larger canvas. They can launch more missions, they can build more ships, but each mission still obeys the same physics. Each ship still crawls through the void at sublight speeds, still ages, still degrades, still arrives at destinations that may have changed beyond recognition during the journey. Galactic-scale energy does not bypass relativistic limits. It does not compress the distance between stars. It does not exempt matter from the laws of thermodynamics. It simply means the civilization can attempt more missions simultaneously, each one individually subject to every constraint that made the trip functionally impossible for a lesser civilization. Even if they exist, the universe itself prevents them from getting here. More energy does not change the speed limit. It does not eliminate time dilation. It does not remove interstellar dust. The rules apply to everyone. Now address the proposals that claim to circumvent physics entirely, rather than merely overpowering it. Warp drives, wormholes, faster-than-light travel. These concepts populate science fiction with such regularity that many people assume they represent genuine scientific possibilities awaiting only sufficient technological advancement. They do not. The warp drive concept, most famously formalized by physicist Miguel Alcubierre in 1994, proposes contracting space in front of a vessel and expanding it behind, creating a bubble of warped space-time that carries the ship faster than light without the ship itself exceeding light speed through its local space. The mathematics are internally consistent within general relativity. The physics, however, are devastating. An Alcubierre drive requires exotic matter with negative energy density to sustain the warp bubble. Negative energy density means matter that weighs less than nothing, that gravitationally repels rather than attracts. No such material has ever been observed. No theoretical framework produces it in usable quantities. The energy required to create and sustain a warp bubble, in early calculations, exceeded the mass energy of the entire observable universe. Later refinements reduced this to merely the mass energy of Jupiter, which remains approximately 10 to the 27th kilograms converted entirely to energy. This is currently unsupported by experimental evidence at every level. It requires materials that do not exist, energies that cannot be produced, and conditions that have never been observed in nature. Calling it speculative is generous. It is a mathematical curiosity within general relativity, not a blueprint for engineering. Wormholes face similar objections. A wormhole or Einstein-Rosen bridge is a theoretical tunnel through space-time connecting two distant points. If stable traversable wormholes could be created and maintained, they would indeed allow instantaneous travel between distant locations. But every known solution to the equations of general relativity that produces a wormhole also requires exotic matter with negative energy density to hold the wormhole open. Without this material, the wormhole collapses faster than any object could pass through it. The same exotic matter that has never been observed, never been produced, and may not be physically possible. Additionally, traversable wormholes would likely violate causality, the principle that causes precede effects. If you can travel instantaneously between distant points, you can, through a straightforward application of special relativity, arrive at your destination before you departed. This creates time travel paradoxes that most physicists regard as strong evidence that traversable wormholes cannot exist. The universe appears to enforce what physicists call the chronology protection conjecture, an as yet unproven but widely suspected principle that the laws of physics conspire to prevent time travel. Wormholes are currently unsupported by experimental evidence and face deep theoretical objections that go beyond mere engineering difficulty. Faster-than-light travel of any kind faces the same fundamental obstacle. Special relativity does not merely say that nothing currently goes faster than light. It says that the structure of space-time forbids it for anything with mass. The speed of light is not a velocity limit in the way that a speed limit on a highway works, where you could theoretically build a faster car but choose not to. It is a structural feature of how space and time relate to each other. As any massive object approaches light speed, the energy required to accelerate it further approaches infinity, not a very large finite number. Actual mathematical infinity. You cannot reach infinity. You cannot exceed it. You cannot engineer around it. The speed of light is the geometry of the universe, and you cannot build a machine that violates geometry. These are not limitations of current knowledge that future discoveries might overturn. They are consequences of the most thoroughly tested theories in the history of physics. Special relativity has been confirmed by every experiment ever designed to test it, across more than a century of increasingly precise measurements. General relativity has been confirmed by gravitational lensing, gravitational waves, the precession of Mercury's orbit, the behavior of GPS satellites, and hundreds of other observations. The speed of light as an absolute limit is not a provisional hypothesis awaiting revision. It is one of the most firmly established facts in all of science. Could future physics reveal something unexpected? In principle, yes. Any scientific conclusion is subject to revision in light of new evidence. But the probability that future discoveries will overturn the speed of light limit is comparable to the probability that future biology will overturn the germ theory of disease. Not zero, but so close to zero that building an argument on it is not open-mindedness. It is wishful thinking, wearing the costume of humility. Even if they exist, the universe itself prevents them from getting here. There is another temporal dimension that the advanced civilization argument consistently fails to address. Civilizations do not last forever. They rise, they flourish, they decline. They collapse or transform into something unrecognizable. Human history provides ample evidence of this cycle, and there is no reason to believe alien civilizations are exempt. The window during which a civilization possesses the technology to attempt interstellar travel may be remarkably narrow. Humanity has been an industrial, electronically communicating species for roughly 250 years. We are the only example we know. If that window is typical or even generous, then the period of interstellar capability is a brief flash against the billions of years a planet may orbit its star. A civilization must develop the technology, muster the resources, and launch the mission within that flash, or the opportunity closes forever. Interstellar travel at achievable velocities requires mission durations of thousands to tens of thousands of years. This means the mission must outlast the civilization that launches it, not by a small margin. By orders of magnitude, a civilization that has existed for 10,000 years, already an extraordinarily long-lived society by any historical standard, he would need to launch a mission that takes 10,000 years to reach a star, 1,000 light-years away at 10% of light speed. The mission duration equals the entire age of the civilization. And this assumes the civilization devotes resources to the mission from its very inception and maintains commitment across its entire lifespan. In practice, interstellar exploration would be a late-stage endeavor, pursued only after millennia of prior development. The window of capability, the period during which a civilization possesses the technology to launch interstellar missions but has not yet declined or transformed, might be remarkably narrow, a few centuries, perhaps a few millennia at most. Now multiply this constraint across the galaxy. If intelligent civilizations are common, many of them may have risen and fallen already. The Milky Way is roughly 13 billion years old. Stars have been forming and dying for most of that history. Planets with conditions suitable for life may have existed for 10 billion years or more. If civilizations arise, flourish, and collapse within windows of a few thousand to a few million years, then the galaxy at any given moment may contain civilizations at vastly different stages of development. Some just discovering fire, some building their first telescopes, some launching their first interstellar probes, some collapsing under the weight of their own complexity, and some already gone, leaving behind nothing but cold ruins on forgotten worlds. The chances that two civilizations exist simultaneously, within communication range of each other, both possessing interstellar capability and both directing their efforts toward the same target, are vanishingly small. The galaxy is vast, the windows of capability are narrow, the distances enforce isolation, and time, the great eraser, ensures that most civilizations will never overlap with their nearest neighbors. Two candle flames burning in a dark cathedral, each lasting only a few seconds, separated by hundreds of feet. The probability that both flames burn at the same moment and that the light from one reaches the other before it flickers out is almost zero. Not because the candles are not real, but because the cathedral is too large and the flames are too brief. Entropy deserves special attention because it represents the ultimate constraint that no technology can overcome. The second law of thermodynamics states that the total entropy of a closed system always increases over time. Order degrades into disorder. Energy disperses from concentrated to diffuse. Complex structures break down into simpler components. This law governs every physical process in the universe without exception. No machine operates at perfect efficiency. No structure maintains itself indefinitely. No system resists entropy forever. For interstellar travel, entropy means that every component of a spacecraft degrades over time. Seals crack, circuits corrode, bearings wear, fuel decays, biological systems accumulate damage. Even the most advanced materials known to physics are subject to atomic-level degradation over sufficient timescales. Radiation damage displaces atoms from crystal lattices. Thermal cycling stresses molecular bonds. Micrometeorite impacts erode surfaces. The interstellar void is not a gentle environment that preserves travelers in amber. It is a slow-motion disassembly line that takes apart everything passing through it, atom by atom, year by year, millennium by millennium. A generation ship travelling for 10,000 years must fight entropy for 10,000 years. Every repair consumes resources. Every replacement part must be manufactured from onboard materials, which are finite. Every system that fails must be fixed before the failure cascades into dependent systems. Over 10,000 years, even systems designed with enormous redundancy will eventually exhaust their reserves. The mathematics of reliability engineering make this clear. A system with a 99.9% annual survival probability, meaning a 1 in 1,000 chance of catastrophic failure in any given year, has only a roughly 0.005% chance of surviving 10,000 years without a single failure. Functionally zero. To achieve even a 50% chance of surviving 10,000 years, the annual failure probability must be less than 1 in 144,000. These are reliability levels that no human technology has ever approached, and they must be maintained not for a single system but for thousands of interdependent systems operating simultaneously in the most hostile environment known. The final proposed solution to the interstellar travel problem is the self-replicating probe, often called a von Neumann probe after mathematician John von Neumann, who first formalized the concept of self-reproducing machines. The idea is compelling. Instead of sending crude ships across the void, a civilization sends a single robotic probe to the nearest star. Upon arrival, the probe uses local resources, asteroids, comets, planetary materials, to construct copies of itself. These copies travel to the next nearest stars and repeat the process. Each generation of probes spreads outward, doubling their numbers with each replication cycle. Even at modest speeds, such a wave of self-replicating probes could theoretically colonize the entire galaxy in a few million years. This concept is the strongest argument for the feasibility of interstellar exploration, and it still fails under scrutiny. Self-replication requires manufacturing capability of extraordinary sophistication. The probe must be able to mine raw materials in alien environments, refine those materials into usable components, and assemble exact copies of itself, including every sensor, every processor, every propulsion element, and every line of its own programming. This is not three-dimensional printing. This is autonomous molecular-scale manufacturing in environments that the probe was not specifically designed for. Every star system presents different resources, different compositions, different challenges. A probe designed to replicate using asteroids in one system may find entirely different asteroid compositions in the next. Replication also introduces mutation. No copying process is perfect. Each generation of probes will contain small errors, deviations from the original design. Over thousands of generations, these errors accumulate. Some probes will malfunction, some will replicate incorrectly, producing defective offspring. Some will lose critical capabilities. The wave of probes spreading across the galaxy becomes increasingly degraded with each generation, subject to the same entropic decay that afflicts every physical system. Natural selection might preserve functional probes and eliminate broken ones, but this assumes the probes operate in environments where selection pressures are consistent, which they are not. Every star system is different. Every replication cycle introduces new variables. The probe swarm evolves in unpredictable directions, drifting further from its original purpose with each generation. And even if self-replicating probes work perfectly, the timescale remains prohibitive. At 1% of light speed, colonizing the galaxy takes roughly 10 million years. At 10% of light speed, roughly 1 million years. These are timeframes that dwarf the lifespan of any known civilization. The civilization that launches the first probe will not exist when the wave reaches distant star systems. The probes become orphans, carrying instructions from a dead culture, arriving at worlds their creators never knew existed, executing a mission whose purpose evaporated millions of years before the first copy reached its destination. The galaxy might eventually be filled with probes, but those probes would be fossils, artifacts of extinct civilizations, drifting through star systems with no one left to receive their reports. Even if they exist, the universe itself prevents them from getting here. Every path leads to the same conclusion. The universe is not merely large, it is structured in a way that enforces isolation. The speed of light creates an absolute ceiling on travel and communication. The energy requirements for relativistic travel create a floor that no civilization can dig beneath. The passage of time erodes ships, crews, civilizations, and purpose with equal indifference. Entropy guarantees that every physical system degrades, and the distances between stars ensure that every journey is measured not in the lifetimes of individuals, but in the lifetimes of entire societies. This conclusion should not be mistaken for pessimism about alien life. Nothing in this analysis suggests that intelligent life is rare or absent in the cosmos. The universe may be saturated with civilizations. Every galaxy might harbor thousands of thinking species, each one building, discovering, wondering, and looking upward at their own unfamiliar constellations. The argument presented here has never been that aliens do not exist. The argument is that the universe is designed, if design is even the right word for the blind architecture of physical law, to keep its inhabitants apart. This realization carries a weight that is difficult to express without slipping into the philosophical territory that this analysis has deliberately avoided until now. But here, at the end, the philosophical dimension deserves its moment, because the implication of everything we have explored is not merely technical, it is existential. If intelligent life is common, if civilizations arise regularly on worlds scattered across the Milky Way, then the most likely state of the galaxy at any given moment is one of profound and permanent isolation. Thousands of civilizations, each one burning briefly against the dark, each one surrounded by distances it cannot cross, energies it cannot muster, and timescales it cannot survive. Not because they are stupid, not because they lack ambition, but because the universe is too large and too slow for its inhabitants to ever find each other. The silence of the cosmos is not evidence that we are alone. It is evidence that the cosmos is very, very large and very, very quiet. Not empty, not hostile, just indifferent. The universe does not prevent life from arising. It prevents life from meeting. It builds walls of light years between every inhabited world and enforces those walls with the most fundamental laws of physics: the speed of light, the conservation of energy, the arrow of entropy, the passage of time. These are not barriers that future science will casually dismantle. They are the architecture of reality, and they apply to every mind that has ever looked up and wondered. The candle flames burn in the cathedral, brief, beautiful, scattered across an immensity that dwarfs them all. Each flame illuminates its own small circle and casts no light beyond it. The darkness between them is not empty. It is simply too vast for any flame to bridge. If intelligent life is common, the universe may simply be too large and too slow for civilizations to ever meet. The barrier is not technology. The barrier is not intelligence. The barrier is not willpower or resources or imagination. The barrier is distance itself.